For our next topic, we're going to talk about how we predict directing effects if we have multiple groups that we need to deal with or multiple aromatic rings with different groups on them. Fortunately for us, this is a fairly simple process. There are two rules that we always follow. Rule number one, the strongest activating group always controls addition. So this is where we get the next substituent. Is it ortho-para or is it meta? And after we apply directing group effects, then we look at steric effects. So when we have a problem like this that we're looking at it, how do we put it all together? What's our process? Step number one, we have to identify each group that's on the aromatic ring. Here we're going to say, is it activating or deactivating? Is it weak, moderate, or strong? Then we identify sterics. So after we've identified which positions are most likely to be substituted, we say where is the position that is least hindered. So most activated and least hindered, that's where substitution occurs. Part number three is let's do the reaction. So put the group on there. All right, so before I hand this off to you to do some practice, I wanted to walk through a full example of how we predict the position that gets substituted next. So again, I'm going to ask you two things. Where do we get substitution? What is the product of the reaction? And for the reaction that we're going to look at, I'm going to brominate meta-nitroisopropylbenzene. So where do we start? I'm going to redraw this here, and I'm going to label my groups. The nitro group is strongly deactivating. The isopropyl group is weakly activating. No matter how strong a deactivating group is, the activating group will always beat it. So the isopropyl group directs substitution to the ortho and the para positions of the ring. Now between those, we have to decide which is least sterically hindered. So the top position is extremely hindered as it's between both of our substituents. The other ortho position is moderately hindered as it's next to the bulky isopropyl group. That means that the para group is going to be the least hindered overall. So when we put that all together, it's the para position on this ring, the position that is para to the isopropyl group that is going to be substituted. Now if I look at my reaction, I can identify the electrophile. So in this case, Br plus is the active electrophile for the reaction. Aluminum tribromide is acting as a catalyst. So in the course of this process, I'm going to produce a substituent. I'm going to substitute the para hydrogen relative to the isopropyl group of the bromide, and that's how we get the major product. All right, now it's your turn. I'm going to show some reactions, and I'm going to give you some time to work through these, and then we'll talk about the products that we get from each reaction. So here's our set of things. Pause the video now, work through each of these problems, take as much time as you want, then come back to this, play it again, and we'll talk through it. All right. So let's take a look at this first nitration reaction. This ring has only one substituent, which is meta-directing. So there's only one possible product that we can get out of the reaction, which is the meta-nitro product. So there's the product from the first reaction. In the second reaction, we have two substituents that we have to look at, an OH group and a nitro group. The OH group is the activating group. It is ortho-para directing. The para position is already occupied by the nitro group, so our substituent is going to have to go to one of the two ortho positions relative to the phenol. This is our major product. Number three, for this ring we have two activating groups, an ester and an alcohol. The alcohol is the stronger group, so I've marked its ortho-para positions because that's where substitution will be most active. In this reaction, SO3 is the active electrophile, so it's going to get substituted at the less sterically hindered para position relative to the alcohol. Oops, and I've shown the wrong reaction here. That should be a sulfonic acid. My apologies. All right, so for this final reaction, I'm going to show the product first. Okay, here's our product. Now the way we get this is in this reaction we actually have two separate aromatic rings. The one to the left is deactivated, the one to the right is activated. So this means that substitution, if we do a reaction, will primarily occur only at the ring on the right. The substituent there is ortho-para-directing, so we mark those positions. Between ortho and para substitution is favored due to steric hindrance, so we get Friedel-Crafts acylation at the less hindered site of the more activated of our two aromatic rings. That will be our major product. Okay, check your work. So as you check your work, what you want to do is you want to go back and look at the process that you took. How did you solve these problems? What did you look at first? What did you look at second? And then work through it to make sure that your process is what's good here, because that's what's important for these types of problems.